Hello and welcome to Space Historians. I'm glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond our world. This is your moment to leave the noise of the day behind and step quietly into the vast, starlit corridors of cosmic history. Each episode here isn't just about stars, it's about the stories they hold, the mysteries whispered by ancient astronomers, and the quiet wonders still waiting. If you enjoy these quiet journeys, a like and a subscribe help keep this channel orbiting. But for now, you don't need to do anything but listen. There is a hole in the universe. Not metaphorically, not poetically, but literally, in the most precise sense astronomy can offer. It stretches across 330 million light-years of space, a vast sphere of near emptiness where galaxies should be but are not. It is called the Boötes Void, and it is one of the largest structures of absence ever discovered. When you first hear this, if it sounds impossible, a hole implies something missing, as though space itself has been carved away. But that is not quite right. The void is not a tear in the fabric of reality, not a gateway to nothing. It is simply a region where matter is astonishingly sparse, where the usual clustering of galaxies gives way to silence. For most of human history, the night sky appeared filled with stars. Ancient peoples saw constellations, patterns that repeated each season, unchanging and eternal. Even when telescopes revealed galaxies beyond our own, the cosmos still felt crowded, packed with light and matter in all directions. The idea that there could be vast regions of near-nothingness seemed absurd. Yet the Boötes Void exists. It sits in the northern constellation of Boötes, the herdsman, a familiar shape to skywatchers marked by the bright orange star Arcturus. In that same general region of sky, when astronomers mapped galaxies in the early 1980s, they expected to find the usual distribution. Clusters connected by filaments, separated by gaps, but never truly vacant. Instead, they found emptiness, a bubble stretching hundreds of millions of light-years across, containing only a few dozen galaxies where thousands should exist. If the void had the same average density as the rest of the universe, it should hold about 10,000 galaxies. The actual count is closer to 60. This is not just unusual, it is extreme. Most cosmic voids measure tens of millions of light-years across. The Boötes Void is an order of magnitude larger, pushing the boundaries of what structure formation theory predicts. Its sheer scale makes it extraordinary, a cavity so vast that entire superclusters could fit inside it with room to spare. What makes this discovery even more remarkable is that the void is not completely empty. A few galaxies drift inside it, isolated specks of light in an ocean of darkness. These lonely systems exist in near solitude, separated from their nearest neighbours by distances that dwarf anything we experience in denser regions of the cosmic web. They are survivors, rare systems that manage to form in conditions of profound scarcity. The void challenges our intuition about how the universe should look. We think of space as filled with galaxies, with structure everywhere we turn our telescopes. But the Boötes Void reveals that absence is just as fundamental as presence. The cosmic web is defined not only by where galaxies cluster, but also by where they do not. To picture this, imagine the universe as a vast sponge. The solid parts represent filaments and clusters where galaxies gather. The holes represent voids where galaxies are rare. The Boötes Void is one of the largest holes in that sponge. A cavity so immense that it shapes the surrounding structure. The filaments that border it are denser because matter has flowed away from the void, accumulating at its edges. This emptiness is not static, it is dynamic, evolving over billions of years as the universe expands. Gravity pulls matter into overdense regions, forming galaxies and clusters. Meanwhile, underdense regions like the Boötes Void lose matter, becoming emptier with time. The expansion of space itself amplifies this process, stretching the void larger and larger. For physicists, the Boötes Void is more than a curiosity. It is a laboratory for testing cosmological models. The standard theory of structure formation predicts that voids should exist, formed naturally from tiny density fluctuations in the early universe. But voids as large as Boötes are rare. They sit at the extreme tail of the statistical distribution, challenging models to explain how such enormous underdensities can arise. The void also raises questions about what we mean by emptiness. In everyday language, empty suggests nothing at all. But in physics, even the most barren regions of space are filled with dark matter, low-density gas, and the quantum foam of virtual particles. The Boötes Void is not truly empty. It is simply emptier than average, defined by what is missing rather than what remains. This distinction matters because it shapes how we interpret the universe. The void is not a mistake or a gap in creation. It is part of the architecture, a natural outcome of the same processes that build galaxies and clusters. Without voids, the cosmic web would not exist in the form we observe. Absence and presence are two sides of the same structure. As you let this thought settle, picture the Boötes Void as it truly is. Not a black hole or a tear in space, but a vast bubble where galaxies are few. Imagine light crossing it, travelling for hundreds of millions of years without encountering much matter. Imagine the few galaxies inside it, drifting in isolation, their stars burning quietly in the darkness. The impossible has become real. A hole in the universe, measured and mapped, sitting in plain sight for anyone who knows where to look. The Boötes Void is one of the most extreme features of the cosmos, and its discovery has transformed how we understand the large-scale structure of everything. The story of the Boötes Void begins not with emptiness, but with a constellation. Boötes, the herdsman, is one of the ancient star patterns visible in the northern sky during spring and summer. Its brightest star, Arcturus, glows orange and red, one of the most luminous stars visible from Earth. To the naked eye, Boötes appears as a kite-shaped pattern, familiar and unchanging across generations. But behind those visible stars lies something far stranger. When astronomers turned their telescopes toward this region in the late 1970s and early 1980s, they were not looking for emptiness. They were conducting systematic surveys of galaxies, mapping the three-dimensional structure of the universe one redshift measurement at a time. The work was painstaking. Each galaxy required careful observation. Its light had to be collected, its spectrum dispersed, and the positions of familiar absorption or emission lines identified. From these measurements, astronomers could calculate how fast the galaxy was receding, and from that recession speed, they could estimate its distance. Plot enough galaxies, and a map of the cosmos begins to emerge. The team leading the survey included Robert Kirshner, Augustus Oemler, Paul Schechter, and Stephen Schechtman. They were working with some of the most powerful instruments available at the time, including telescopes at Kitt Peak National Observatory and Las Campanas Observatory. Their goal was to fill in a portion of the cosmic map, one slice at a time, building a three-dimensional picture of how galaxies were distributed on the largest scales. What they found in Boötes was unexpected. As they plotted galaxy after galaxy, measuring distances and positions, a pattern began to emerge. Or rather, the absence of a pattern. There was a vast region where galaxies simply were not appearing. At first, it seemed like it might be an observational artifact, perhaps a region obscured by dust or mist due to selection effects. But as more data accumulated, the conclusion became unavoidable. They had discovered a void, not just an ordinary one. It was enormous, stretching across hundreds of millions of light years. When they published their findings in 1981, the astronomical community took notice. The Boötes Void, as it came to be known, was among the largest structures of emptiness ever recorded. The discovery was possible only because of redshift surveys. Before such surveys, astronomers could see galaxies scattered across the sky, but they had no way to know which were nearby and which were distant. Everything appeared projected onto the two-dimensional dome of the sky. Redshifts changed that, adding depth to the picture, revealing that galaxies were not randomly scattered but arranged in patterns. The Boötes Void stood out dramatically because of its scale and its spherical shape. Most voids are irregular, stretched and distorted by surrounding structures, but Boötes appeared almost perfectly round, a bubble carved out of the cosmic web. This symmetry made it easier to identify and harder to dismiss as an artifact. The void sits at a distance of about 700 million light-years from Earth, placing it well beyond our local neighbourhood, but still within reach of modern instruments. Its coordinates in the sky are straightforward to locate for anyone with a star chart and a telescope. Though what you see when you look there are the few faint galaxies that populate its edges and interior. The region of Boötes itself offers no visual clue to the void's existence. The stars of the constellation shine as brightly as they ever have. The orange glow of Arcturus dominates the pattern, but behind and beyond those stars, stretching across vast distances invisible to the naked eye, lies the cavity that changed cosmology. What makes the location of the void significant is not just where it sits in space, but when it was discovered. The early 1980s were a time of rapid progress in observational cosmology. Telescopes were improving, detectors were becoming more sensitive, and computers were beginning to handle the large data sets required for mapping the universe. The Boötes Void was one of the first dramatic examples of what these new tools could reveal. Before its discovery, cosmologists knew that galaxies clustered together, forming groups and clusters, but the flip side of clustering, the voids where galaxies were absent, had not been fully appreciated. The Boötes Void made it impossible to ignore. It showed that the universe was not just a collection of galaxies sprinkled across space, but a web of structures where presence and absence were equally important. The constellation Boötes, named for a herdsman in Greek mythology, became associated with one of the most profound discoveries about cosmic structure. The herdsman now watches over not just his cattle, but a vast emptiness that stretches far beyond anything the ancients could have imagined. The surveys that revealed the void were modest by today's standards. Only a few hundred galaxies were measured in the initial discovery. But that was enough to see the whole. Later surveys, with thousands and then millions of galaxies mapped, confirmed the void's existence and refined its boundaries. Each new data set showed the same feature, a spherical underdensity centered in Boötes. The location also matters because it sits in a region accessible to Northern Hemisphere observatories. This made follow-up observations easier, allowing astronomers to study the void in greater detail. Over the decades, the Boötes Void has been observed with increasingly powerful instruments, from ground-based telescopes to space-based observatories, each adding layers of information about its properties. As you rest now, picture that region of sky. The constellation Boötes, visible on a spring evening, its stars forming a familiar pattern, and behind those stars, hidden from view but mapped by light stretched across billions of years, a cavity so vast that it defies easy comprehension. The void began here, in a patch of sky named for a herdsman, where careful observers noticed what was missing. The first hint of the Boötes Void came not from seeing something, but from noticing an absence. When astronomers plotted the galaxies they had measured in the region of Boötes, they expected to see a fairly even distribution, perhaps with some clustering here and there. What they saw instead was a gap, a region where almost no galaxies appeared. At first this seemed strange, but not necessarily significant. Surveys are always incomplete. Perhaps they had simply missed galaxies in that region due to observational limits. Perhaps dust was obscuring the view. Perhaps the selection criteria had inadvertently excluded certain types of galaxies. These are the kinds of questions astronomers always ask when they see something unexpected. But as more data came in, the gap persisted. It was not an artifact of missing data. It was real. The region genuinely contained far fewer galaxies than the surrounding areas. This was the spark of mystery, the moment when absence became a discovery. Redshift measurements were key to understanding what they were seeing. When light from a galaxy travels through the expanding universe, its wavelength is stretched, shifting toward the red end of the spectrum. The amount of shift tells astronomers how fast the galaxy is receding, which in turn reveals its distance. By measuring redshifts for hundreds of galaxies, the team could build a three-dimensional map, not just of where galaxies appeared on the sky, but of where they sat in space. When those measurements were plotted in 3 dimensions, the Boötes Void emerged clearly. It was not just a gap on the sky, but a spherical region of space where galaxies were missing. The void had depth, volume, and structure. It was not a line of sight effect, but a genuine underdensity extending in all directions. The spark of mystery was this: how could such a large region exist with so few galaxies? The universe, on average, is remarkably uniform. The cosmic microwave background shows that at early times, density variations were only about 1 part in 100,000. Over billions of years, gravity amplified those small fluctuations, pulling matter into denser regions and leaving voids behind. But the Boötes Void was so large that it challenged expectations. If the initial fluctuations were truly random and Gaussian, as inflation predicts, then structures like the Boötes Void should be rare but not impossible. They would sit at the extreme tail of the probability distribution. The fact that such a void existed was not necessarily a problem for theory, but it was close to the edge of what models predicted. This tension between observation and expectation is what made the discovery intriguing. The mystery deepened when astronomers realized just how empty the void was. A region of that size should contain thousands of galaxies if it had average density. Instead, careful surveys found only a few dozen. This was not just a slight underdensity, it was a profound one, with the void containing less than 1% of the expected number of galaxies. What happened to all that matter? The answer lies in the dynamics of structure formation. In the early universe, regions that were slightly less dense than average expanded faster than the cosmic mean. Matter flowed out of them, attracted by the gravitational pull of denser regions nearby. Over billions of years, this process hollowed out the underdense regions, creating voids. The Boötes Void formed this way, beginning as a small fluctuation in density, barely perceptible in the early universe. As time passed, gravity worked its slow magic, pulling matter away from the underdense region and into the filaments and clusters that bordered it. The void grew larger and emptier, while the surrounding walls grew denser and more populated. But the scale of the Boötes Void suggested that its initial underdensity must have been unusually large, or that the dynamics of its growth were particularly efficient. Either way, it represented an extreme case, one that tested whether cosmological models could reproduce such features. The spark of mystery also ignited questions about what the void meant for our understanding of the universe. If voids this large were common, it would suggest that the cosmic web was more structured than anyone had realized. If they were rare, it would confirm that Boötes was a statistical outlier, an unlikely but natural outcome of random fluctuations. For the astronomers who first noticed the gap, the mystery was also personal. They had stumbled upon something unexpected, something that forced them to rethink assumptions. The void was not just a hole in the data, it was a window into how the universe organized itself on the largest scales. The few galaxies that did exist inside the void added another layer to the mystery. Why were they there at all? If the region was so underdense, how did these systems manage to form? The answer is that even in voids, small density peaks can exist, rare fluctuations within the larger underdensity. These peaks became the seeds for the isolated galaxies found inside Boötes. Studying these galaxies revealed that they were different from their counterparts in denser regions. They were often smaller, bluer, and more actively forming stars. Their isolation had protected them from the disruptive interactions common in clusters, allowing them to evolve more gently. The void, far from being an empty wasteland, was a unique environment that shaped galaxy evolution in unexpected ways. The spark of mystery, then, was not just about the void itself, but about what it revealed. It showed that absence could be as informative as presence, that emptiness had structure and dynamics, and that the universe was more complex than simple models suggested. The Boötes Void was a puzzle, and solving it required understanding not just where galaxies were, but why they were not elsewhere. As you let this thought rest, imagine those early astronomers plotting their data, watching the gap appear and grow as more galaxies were measured. Picture the moment when they realized it was real, when the mystery crystallized into a discovery. The Boötes Void had revealed itself, and cosmology would never be quite the same. When the discovery of the Boötes Void was first announced, The reaction from the astronomical community was a mixture of fascination and skepticism. The idea that such an enormous region of space could be nearly devoid of galaxies seemed almost too strange to be true. How could emptiness on this scale exist in a universe that appeared so richly populated with matter? For decades, astronomers had been mapping the distribution of galaxies, and while they knew that galaxies clustered together in groups and superclusters, the flip side of that clustering had not been fully appreciated. Voids were expected in theory, regions where matter was less dense than average, but a void spanning 330 million light-years was something else entirely. Some scientists questioned the measurements. Were the redshifts accurate? Could there be systematic errors in the distance estimates? Perhaps the void was not as empty as it appeared. Maybe fainter galaxies had been missed, hidden below the detection threshold of the instruments used. These were reasonable concerns, the kind that always arise when a surprising result challenges expectations. But as more data accumulated, the reality of the void became harder to deny. Independent observations confirmed the initial findings. The gap in the distribution of galaxies was real, consistent across different surveys and different observing programs. The Boötes Void was not an artifact of incomplete data or observational bias. It was genuinely there, a vast bubble of near emptiness carved into the cosmic web. For those who accepted the discovery, the response was awe. The sheer scale of the void was difficult to comprehend. 330 million light-years is a distance so vast that even travelling at the speed of light, it would take that many years to cross. To put it in perspective, the entire observable universe is about 93 billion light-years across. The Boötes Void occupied a significant fraction of that immensity. What made the discovery even more striking was its shape. Unlike many cosmic structures, which are irregular and asymmetric, the Boötes Void appeared nearly spherical. This symmetry was unexpected and beautiful in its own way, suggesting that the processes that carved out the void operated uniformly in all directions. The void was not a random gap, but a structured feature with clear boundaries. The awe extended beyond the scientific community. When news of the void reached the public, it captured imaginations. Here was a hole in the universe, a place where galaxies simply were not. It sounded like science fiction, like something that should not exist. And yet it did, mapped and measured, sitting in a familiar constellation visible from Earth. For cosmologists, the discovery prompted a reassessment of theories about structure formation. The standard models, based on the idea that tiny fluctuations in the early universe grew under gravity to form galaxies and clusters, had to be tested against this extreme example. Could those models produce voids as large as Boötes? If not, it might indicate that something was missing from the theory. Early simulations suggested that yes, such voids were possible, though rare. In a universe seeded with random Gaussian fluctuations, as predicted by inflation, there would occasionally be regions that began with lower than average density. Over time, those regions would expand and empty out, creating voids. The Boötes Void fit this picture, sitting at the edge of the statistical distribution but not beyond it. This was reassuring, but it also meant that the void was a valuable test case. It was rare enough to be interesting, but not so rare as to be impossible. It pushed the models to their limits, forcing theorists to ensure that their simulations could reproduce not just typical structures, but also the extremes. There was also a philosophical dimension to the response. The Boötes Void challenged the assumption that the universe was fundamentally about presence, about matter and energy filling space. Instead, it revealed that absence was equally important. The cosmic web was defined not just by where galaxies were, but by where they were not. Emptiness had structure, had dynamics, had meaning. For some, this was unsettling. The void represented a kind of cosmic loneliness, a reminder that even in a universe filled with hundreds of billions of galaxies, there were vast regions where isolation reigned. The few galaxies inside Boötes were separated from their neighbours by distances that dwarfed anything in denser regions. They existed in near solitude, their stars burning quietly in the darkness. But for others, the void was inspiring. It showed that the universe was more complex and more interesting than simple models suggested. It revealed patterns on the largest scales, structures that connected the smallest quantum fluctuations in the early universe to the immense voids and filaments visible today. The Boötes Void was a link in that chain, a piece of the cosmic puzzle. The disbelief faded as evidence mounted. Follow-up surveys confirmed the void's properties, measuring its size, its depth, and the few galaxies within it. Observations with different instruments and different techniques all pointed to the same conclusion. The void was real, and it was as large and as empty as the initial measurements suggested. What remained was the awe. Even for astronomers who had spent careers studying the cosmos, the Boötes Void was something special. It was a reminder that the universe could still surprise, that there were discoveries waiting to be made simply by looking carefully at the data. It showed that emptiness itself was a subject worthy of study, not just as a backdrop but as an active participant in cosmic evolution. As you consider this, picture the moment when the void's reality sank in. Imagine the astronomers gathering at conferences, discussing the implications, debating the measurements. Imagine the shift from skepticism to acceptance, from disbelief to awe. The Boötes Void had revealed itself, and the universe had become stranger and more wonderful for it. The discovery also highlighted the importance of systematic surveys. Without the patient work of mapping, galaxies one by one, measuring redshifts, and building three-dimensional maps, the void would have remained invisible. It was only through careful observation and meticulous data collection that the absence could be seen. The Boötes Void was a triumph of observational astronomy, a reminder that looking at the sky with fresh eyes could still yield profound discoveries. In the end, the response to the Boötes Void was a blend of scientific rigour and human wonder. The data had to be checked and verified, the implications explored and debated, but beneath all that was a simple recognition. The universe had shown us something extraordinary. A hole in space, vast and nearly empty, sitting quietly in the constellation Boötes, waiting to be understood. The Boötes Void sits at an uncomfortable intersection between what science can explain and what still feels deeply mysterious. On one hand, cosmological models based on well-established physics can account for its existence. On the other hand, its sheer scale and emptiness continue to inspire questions that push at the edges of understanding. This tension between explanation and wonder is what makes the void so compelling. The scientific explanation begins with the early universe. In the first moments after the Big Bang, space was filled with matter and energy, distributed almost uniformly. Almost, but not quite. Tiny fluctuations in density, seeded by quantum processes during cosmic inflation, created regions that were slightly more or less dense than average. These fluctuations were incredibly small, only about 1 part in 100,000. Regions that were slightly denser attracted more matter, growing denser still. Regions that were slightly less dense lost matter as it flowed toward the overdense areas. This process, known as gravitational instability, transformed the nearly smooth early universe into the cosmic web we see today, with filaments, clusters, and voids. The Boötes Void formed this way. It began as a region where the initial density was slightly lower than average. As time passed, matter drained out of it, pulled by the gravitational attraction of surrounding filaments. The void expanded, becoming larger and emptier. Meanwhile, the matter that left accumulated at the boundaries, forming the walls of galaxies that now surround the void. This explanation is elegant and consistent with observations. Simulations that start from the conditions seen in the cosmic microwave background can produce voids like Boötes. The standard model of cosmology, with its combination of dark matter, dark energy, and ordinary matter, predicts that such structures should exist, though rarely. But this scientific understanding does not eliminate the mystery. How can something so large arise from fluctuations so small? The initial underdensity that seeded the Boötes Void was minuscule, barely perceptible even in the most sensitive measurements of the early universe. Yet over billions of years, it grew into a cavity spanning hundreds of millions of light-years. The amplification is immense, and while we understand the process, the result still feels improbable. There is also the question of rarity. The Boötes Void sits at the extreme end of the size distribution for voids. Most voids are tens of millions of light-years across. Voids larger than 100 million light-years are uncommon. The Boötes Void, at over 300 million light-years, is exceptional. This raises the question, is it simply a statistical fluke, or does its existence hint at something we have not fully understood about structure formation? The mystery deepens when we consider what the void contains. It is not completely empty. About 60 galaxies have been identified inside it, scattered across its volume. Where did these galaxies come from? If the void is so underdense, how did even these few systems manage to form? The answer is that within the larger underdensity, there were smaller peaks in the density field, rare fluctuations within the void itself. These peaks became the seeds for the isolated galaxies, but this explanation, while scientifically sound, feels incomplete. The galaxies inside the void are strange. They are often smaller, bluer, and more actively forming stars than galaxies in denser regions. Their isolation has shaped their evolution in ways we are only beginning to understand. They are survivors, rare systems that tell a different story about how galaxies grow. The void also challenges our intuition about what emptiness means. In everyday language, empty suggests nothing at all. But in physics, even the Boötes Void is filled with dark matter, low-density gas, and the quantum vacuum. The void is not truly empty. It is simply emptier than average. This distinction is important scientifically, but it does not resolve the deeper mystery of why such extremes exist. There is also the question of what the void reveals about the universe's initial conditions. The fluctuations that seeded structure were supposed to be random, drawn from a Gaussian distribution with well-defined statistical properties. The Boötes Void, being so large, tests whether that assumption holds. If voids like Boötes were too common, it would suggest the initial fluctuations were not quite Gaussian, hinting at exotic physics during inflation. If they were too rare, it might indicate our models were missing something. So far, the observations are consistent with the standard picture. The Boötes Void is rare, but not impossibly so. It fits within the predictions, sitting at the tail of the distribution but not beyond it. This is reassuring, but it also means the void remains on the edge, a structure that challenges models without quite breaking them. The tension between science and mystery is also about perspective. From the standpoint of cosmological theory, the Boötes Void is explained. It is a natural outcome of gravitational instability, acting on initial fluctuations. From the standpoint of human experience, it remains deeply mysterious. How can emptiness be so vast? How can absence be so structured? These questions are not scientific in the narrow sense, but they arise naturally from contemplating the void. The void also raises questions about what we do not see. Dark matter and dark energy, which together make up 95% of the universe's content, are invisible. We infer their presence from their effects on visible matter. In the Boötes Void, dark matter is present but sparse, and dark energy drives the accelerated expansion that stretches the void ever larger. These unseen components shape the void just as much as the visible galaxies, yet we cannot observe them directly. The mystery of the void is intertwined with the mystery of the dark universe. As you rest with this tension, imagine the Boötes Void as a place where science and mystery meet. It can be explained with equations, simulated on computers, and measured with telescopes. But it also remains strange, a hole in space that defies easy comprehension. The void is both understood and unknowable, both ordinary and extraordinary. It sits at the boundary where knowledge meets wonder, where the universe reveals itself and yet remains elusive. When confronted with something as unusual as the Boötes Void, scientists do not always agree on what it means. The discovery sparked debates that continue to this day, not about whether the void exists, but about what it reveals. Different minds brought different perspectives, and those perspectives shaped how the void was interpreted and studied. One group of astronomers saw the Boötes Void as confirmation of the standard cosmological model. According to this view, the void was exactly what theory predicted. Structure formation begins with small random fluctuations in the early universe, and over time, gravity amplifies those fluctuations into the cosmic web. Voids are a natural part of that web, regions where the initial density was lower than average. The Boötes Void, while large, was simply an extreme example of a common phenomenon. This perspective was supported by simulations. When cosmologists ran computer models starting from conditions consistent with the cosmic microwave background, voids naturally emerged. Most were small, but occasionally large ones appeared. The statistics of these simulated voids matched the observations reasonably well. The Boötes Void fit within the expected distribution, rare but not impossible. For those who held this view, the void was a success story for cosmology, proof that the models worked even at extreme scales. But not everyone agreed. Another group of scientists saw the Boötes Void as a challenge, a structure that pushed the limits of what theory could comfortably explain. While simulations could produce voids of similar size, they did so rarely. The probability of finding a void as large as Boötes in a volume the size of the observable universe was low, though not negligible. This raised the question: was Boötes simply a lucky observation, or was it hinting at something unexpected? Some theorists proposed that the void might indicate a problem with the initial conditions. If the fluctuations seeded during inflation were not perfectly Gaussian, or if there were subtle deviations from the standard spectrum, it might make large voids more common than expected. Detecting such deviations would have profound implications, potentially revealing new physics in the earliest moments of the universe. Others suggested that the Boötes Void might reflect uncertainties in how we understand dark matter or dark energy. If dark matter behaved differently than assumed, perhaps interacting with itself in ways we had not considered, it could change how voids form and grow. If dark energy varied in strength over time or across space, accelerate the expansion of voids more than predicted. The void became a test case for these alternative ideas. There was also debate about how to define and measure voids. Different algorithms for identifying voids in galaxy surveys produce slightly different results. Some methods emphasize size, others emphasize depth of underdensity. The Boötes Void was robust across most definitions, but the details varied. This led to disagreements about its exact properties, its true size, and how it compared to other voids. The few galaxies inside the void also became a point of discussion. Some astronomers argued that their presence proved the void was not as empty as claimed, that it contained more structure than initial reports suggested. Others countered that the galaxies were so sparse, they only reinforced how extreme the underdensity was. The debate was not just about numbers, but about interpretation. What did those isolated galaxies reveal about how voids form and evolve? The division of minds also reflected broader tensions in cosmology. The standard model, with its reliance on dark matter and dark energy, had proven remarkably successful at explaining observations, but it left fundamental questions unanswered. What is dark matter? What is dark energy? The Boötes Void, as an extreme structure, became a focal point for those who hoped to find cracks in the standard model, places where new physics might emerge. Some researchers proposed alternative theories of gravity to explain cosmic acceleration without invoking dark energy. In these modified gravity models, the behavior of voids could differ subtly from predictions based on general relativity. The Boötes Void, with its large size and clear boundaries, was an ideal place to test such ideas. By measuring the motions of galaxies near the void's edges, astronomers could look for deviations from expected behavior. Others focused on the role of cosmic variance. The universe we observe is only one realization of a statistical process. Even if the Boötes Void is rare, it is not impossible that we happen to see one. This argument suggested that the void did not require exotic explanations, only patience and acceptance that rare events do occur. The division here was not about physics, but about how to interpret rarity. There were also philosophical divisions. Some scientists saw the void as evidence that the universe is fundamentally structured, that absence and presence are equally important in defining the cosmic web. Others saw it as a curiosity, interesting but not fundamental, a detail in the larger story of how galaxies cluster. These differing views shaped research priorities and the kinds of questions asked. Despite these divisions, there was broad agreement on one point. The Boötes Void was important. Whether it confirmed the standard model or challenged it, whether it was typical or exceptional, it provided a valuable test case. Studying the void pushed observational techniques, inspired new simulations, and forced theorists to refine their predictions. The disagreements were not obstacles but engines of progress, driving deeper understanding. The debates also highlighted the collaborative nature of science. While minds divided on interpretation, they united in the effort to gather better data. New surveys were proposed, more sensitive instruments designed, and more sophisticated simulations run. The Boötes Void became a benchmark, a structure that every cosmological model had to account for. As you consider these divisions, imagine the conferences and seminars where scientists presented competing views. Picture the papers written, the data analysed, the models tested. The Boötes Void was not just a hole in space, but a focal point for some of the deepest questions in cosmology. The divisions of minds were not failures of consensus, but expressions of the richness of inquiry. Different perspectives illuminated different facets of the same mystery. In the end, the Boötes Void taught cosmologists humility. It showed that even well-established theories have edges, places where predictions become uncertain and observations surprise. It reminded everyone that the universe is complex, that extreme structures exist, and that understanding requires both rigour and openness. The void divided minds, but it also united them in the shared quest to comprehend the cosmos. Once the Boötes Void was discovered, the next question became urgent. What exactly are we looking at? How large is it truly? How empty? What lies at its boundaries? Answering these questions required a systematic pursuit, years of careful observation and measurement, building a complete picture of one of the universe's most extreme structures. The pursuit began with more redshift surveys. The initial discovery had been based on a few hundred galaxy measurements, enough to reveal the void but not enough to map it in detail. Astronomers needed to measure thousands more galaxies in and around the region, building a three-dimensional map with sufficient resolution to trace the void's boundaries and identify any structure within it. This was painstaking work. Each galaxy required its own observation. Light had to be collected, often through long exposures lasting hours. Spectra had to be recorded, the wavelengths of familiar emission and absorption lines measured with precision. From those measurements, redshifts could be calculated, and from redshifts, distances. One galaxy at a time, the map grew more complete. The pursuit was not just about quantity, but quality. Faint galaxies, easily missed in shallow surveys, had to be detected. Dwarf galaxies, small and dim, could be hiding in the void, and finding them would change the picture of how empty it truly was. Deep imaging campaigns were launched, pushing telescopes to their limits to capture the faintest glimmers of light. As more data accumulated, the shape of the void became clearer. It was, not perfectly spherical, as early observations suggested, but slightly elongated, stretched along one axis. This asymmetry hinted at the influence of surrounding structures, filaments pulling on the void's boundaries, distorting its shape. The pursuit revealed that even emptiness has contours, shaped by the gravitational tides of the cosmic web. The size of the void also came into focus. Early estimates placed it at around 300 million light-years across, but as more galaxies were measured, refinements were made. Different definitions of where the void ended and the filaments began produced slightly different numbers, but the scale remained consistent. The Boötes Void was enormous, one of the largest known underdensities in the universe. Mapping the interior was equally important. The few dozen galaxies found inside the void were studied in detail. Their spectra revealed their compositions, their colours indicated their ages and star formation rates, and their positions showed whether they were clustered or truly isolated. The pursuit showed that these void galaxies were different, bluer and more gas-rich than their counterparts in denser regions, shaped by their solitude. The boundaries of the void became a focus of intense interest. At the edges, where the void transitioned into surrounding filaments, galaxy density increased sharply. These walls of galaxies marked the places where matter had accumulated, pulled away from the void's interior by gravity. Measuring the properties of these boundary galaxies revealed how the void had grown, how matter flowed outward over billions of years. Velocity measurements added another dimension to the pursuit. By observing the Doppler shifts of galaxies near the void's edges, astronomers could detect their peculiar velocities, the motions beyond the general expansion of the universe. These velocities revealed that galaxies were indeed streaming away from the void's centre, pushed by the gravitational imbalance created by the underdensity. The void was not static, but dynamic, still expanding. The pursuit also involved simulations. Computer models allowed cosmologists to test whether the standard theory of structure formation could produce voids like Boötes. Starting from initial conditions based on the cosmic microwave background, simulations evolved billions of particles under gravity, creating virtual universes. In these simulations, voids appeared naturally, and occasionally, large ones emerged. Comparing simulated voids to the real Boötes Void helped validate the models and refine predictions. Different observational techniques were brought to bear. Optical telescopes mapped visible light from galaxies. Radio telescopes detected the 21-centimetre emission line of neutral hydrogen, revealing gas reservoirs that optical surveys might miss. Infrared observations penetrated dust, uncovering galaxies hidden from view. Each wavelength added pieces to the puzzle. Gravitational lensing offered another tool. Though the effect is weak in under-dense regions, careful measurements of how background galaxies are distorted by the void's mass distribution provided an independent check on how empty it truly was. These measurements confirmed that the void was under-dense not just in galaxies, but in total matter, including dark matter. The pursuit extended beyond the Boötes Void itself. Astronomers began cataloguing other voids, building databases of hundreds of underdense regions across the sky. By comparing Boötes to this population, they could see how exceptional it was, where it fit in the distribution of void sizes and depths. The pursuit became part of a larger effort to understand voids as a class of structures. Over the years, new instruments joined the pursuit. The Sloan Digital Sky Survey, with its wide field imaging and spectroscopy, mapped millions of galaxies, including many in and around the Boötes Void. Space-based telescopes like Hubble captured high-resolution images of the faintest void galaxies. Each new data set refined the picture. The pursuit also involved theoretical work. Models of void formation were refined, taking into account the effects of dark energy, which accelerates cosmic expansion and influences how voids grow. Predictions were made about how the void should evolve over time, how its boundaries should sharpen, and how its interior should empty further. These predictions could be tested against observations. Measuring the void's imprint on the cosmic microwave background became a goal. Photons from the early universe, passing through the void on their way to us, should experience a slight shift in energy due to the integrated Sachs-Wolf effect. Detecting this required correlating void positions with temperature maps of the microwave background, a subtle signal buried in noise. The pursuit pushed observational techniques to their limits. As you rest with this, imagine the decades of work that went into understanding the Boötes Void. Picture the telescopes scattered across the world, each gathering light from distant galaxies. Picture the computers running simulations, evolving virtual universes. Picture the astronomers analysing data, refining measurements, building maps. The pursuit was slow, methodical, and patient, driven by the desire to understand one of the universe's most extreme features. The Boötes Void did not reveal its secrets quickly. Each answer led to new questions. Each measurement refined the picture but also highlighted uncertainties. The pursuit continues today, with new surveys and new instruments promising even deeper views. The void remains a target, a structure that challenges and rewards those who seek to comprehend it. Understanding the Boötes Void required piecing together clues from multiple sources. Fragments of evidence that, when assembled, revealed the nature of this cosmic emptiness. No single observation could capture the full picture. Instead, astronomers had to weave together data from different wavelengths, different techniques, and different perspectives, building a coherent story from scattered pieces. The most fundamental clue was the redshift data. By measuring how light from galaxies was stretched by cosmic expansion, astronomers could determine distances. Plotting these distances in 3 dimensions revealed the void as a spherical underdensity, a bubble in the distribution of galaxies. This was the first and most important fragment, the evidence that the void was real and not an artifact. But redshifts alone did not tell the whole story. They revealed where galaxies were, but not what those galaxies were like. Spectroscopy provided additional clues. By analysing the light from void galaxies in detail, astronomers could identify specific emission and absorption lines, signatures of different elements and molecules. These lines revealed the chemical composition of the galaxies, their ages, and their star formation, histories. The spectra showed that void galaxies were often rich in hydrogen and helium, with lower abundances of heavier elements compared to galaxies in denser regions. This suggested they had formed fewer generations of stars, that their evolution had been slower and gentler. The isolation of the void had preserved them in a state closer to their origins. Colour measurements added another clue. Astronomers measured the brightness of galaxies at different wavelengths, from ultraviolet through visible light to infrared. The colours revealed the types of stars present. Blue galaxies contained young, hot stars actively forming from gas. Red galaxies were dominated by older, cooler stars, their star formation largely shut down. Void galaxies tended toward the blue end of the spectrum, indicating ongoing star formation. This was unexpected. In denser regions, many galaxies are red and dead, their star formation quenched by interactions with neighbours or by the hot gas-filling galaxy, clusters. In the void, galaxies retained their gas and continued forming stars. The clue suggested that environment mattered, that isolation allowed different evolutionary paths. Radio observations provided fragments of a different kind. The 21 centimetre emission line of neutral hydrogen revealed the gas content of void galaxies. These observations showed extended reservoirs of hydrogen surrounding many systems, far more gas than their counterparts in clusters. The void galaxies were fuel-rich, with the material needed to form stars for billions of years to come. Infrared observations pierced through dust, revealing galaxies that might be hidden in optical surveys. Some void galaxies, though faint in visible light, glowed brightly in infrared, indicating active star formation shrouded by dust. These hidden systems added to the census, refining estimates of how many galaxies the void truly contained. Gravitational lensing offered a subtle but powerful clue. When light from distant galaxies passes through a region of space, its path is bent by the gravitational influence of matter along the way. In dense clusters, this bending is strong, creating dramatic arcs and multiple images. In voids, the bending is weaker, producing only slight distortions. By carefully measuring these distortions across many background galaxies, astronomers could infer the total mass distribution, including dark matter. The lensing data confirmed what galaxy counts suggested. The Boötes Void was underdense in total matter. Not just in visible galaxies. Dark matter, which normally dominates the mass budget, was also sparse in the void. This was important because it showed that the void was not simply a region where galaxy formation had failed. It was genuinely underdense at a fundamental level. The cosmic microwave background provided another fragment. Though the signal was faint, cross-correlating the positions of voids with temperature maps of the background radiation revealed a slight cold spot associated with the void. This was the integrated Sachs-Wolf effect, a signature of photons losing energy as they traversed the expanding void. The detection was marginal, requiring stacking many voids together, but it added to the weight of evidence. Each clue, taken alone, was a piece of the puzzle. Red shifts showed where galaxies were. Spectra showed what they were made of. Colours revealed their ages. Radio data mapped their gas. Lensing measured their mass. The microwave background carried the imprint of their influence on ancient light. Together, these fragments built a comprehensive picture of the void. The boundaries of the void provided their own clues. At the edges, galaxy density increased sharply, transitioning from the sparse interior to the dense filaments beyond. This transition was not gradual but relatively abrupt, suggesting that the void had clear structural boundaries. Measuring the thickness of this transition zone revealed how matter had flowed during the void's formation. Velocity measurements added dynamical clues. By observing the Doppler shifts of galaxies near the void's boundaries, astronomers detected peculiar velocities directed away from the centre. Galaxies were streaming outward, consistent with the void's expansion. This motion confirmed that the void was not a static feature, but an evolving structure, still growing as the universe expands. The few galaxies inside the void were clues in themselves. Their positions, clustered in small groups or isolated entirely, revealed the fine structure within the underdensity. Even in a region as empty as Boötes, small density peaks existed, rare fluctuations within the larger void. These peaks became the sites where galaxies formed, survivors in an environment of scarcity. Historical data provided temporal clues. By comparing observations of the void at different times, astronomers could search for changes. Had galaxies moved? Had new systems formed? While the timescales were too short to see dramatic evolution, the measurements set constraints on how quickly the void was growing and how its galaxies were evolving. All of these clues had to be assembled carefully, accounting for uncertainties and systematic errors. Measurements from different telescopes had to be calibrated consistently. Data from different wavelengths had to be matched galaxy by galaxy. Statistical methods were applied to ensure that apparent patterns were not artifacts of noise. As you consider these fragments, imagine the detective work involved. Each clue pointed in a direction, suggesting a piece of the story. Together, they painted a portrait of the Boötes Void as a vast, under-dense region shaped by billions of years of cosmic evolution. Populated by a few isolated galaxies, bounded by dense walls, and still expanding under the influence of dark energy. The clues were scattered across wavelengths and techniques, but patience and care brought them together. Beneath the visible structure of the Boötes Void lies a deeper mystery, one that involves the invisible components of the universe, dark matter and dark energy. These two substances, which together make up 95% of the cosmic content, shape the void just as much as the galaxies we can see. Understanding the void requires understanding these hidden forces. Dark matter is the gravitational scaffolding of the universe. It does not emit or absorb light, making it invisible to telescopes, but its gravitational influence is unmistakable. Galaxies rotate too quickly to be held together by visible matter alone. Clusters are bound by more mass than their stars and gas can account for. The distribution of galaxies on large scales follows patterns set by dark matter, not by ordinary matter. In the Boötes Void, dark matter is present but sparse. The same processes that emptied the void of galaxies also emptied it of dark matter. In the early universe, regions that were slightly under dense in total matter lost both ordinary matter and dark matter to surrounding overdensities. Over billions of years, this flow carved out the void, leaving behind a region where dark matter halos are rare and small. The few galaxies inside the void sit in these rare dark matter halos. Each galaxy is embedded in a halo of invisible matter, perhaps 10 times more massive than the visible stars and gas. These halos formed from the small density peaks that existed within the larger underdensity of the void. They are survivors, the rare sites where conditions allowed dark matter to clump and pull in enough ordinary matter to form a galaxy. Measuring dark matter in voids is challenging because the signal is weak. Gravitational lensing, which bends the light of background galaxies, provides the most direct evidence. In dense clusters, lensing is strong, creating dramatic distortions. In voids, the effect is subtle, requiring careful statistical analysis to detect. When astronomers stack the lensing signals from many voids, they find that voids are indeed underdense in dark matter, confirming that the emptiness extends beyond visible galaxies to the fundamental matter distribution. Dark energy, the other invisible component, plays a different role. While dark matter pulls, clumping under gravity, dark energy pushes, driving the accelerated expansion of the universe. Discovered in the late 1990s through observations of distant supernovae, dark energy has become one of the greatest mysteries in cosmology. We know it exists because the universe's expansion is speeding up, but we do not know what it is. Voids are particularly sensitive to dark energy because they lack the gravitational resistance of denser regions. In clusters and filaments, the pull of gravity counteracts cosmic expansion, holding structures together. In voids, gravity is weak and expansion proceeds more freely. Dark energy amplifies this effect, causing voids to expand faster than the overall universe. The Boötes Void has been growing for billions of years, and dark energy has accelerated that growth, especially in recent cosmic time. A few billion years ago, dark energy began to dominate the universe's energy budget, overtaking matter and driving acceleration. Since then, voids have expanded more quickly, their interiors becoming emptier as galaxies at the boundaries are pushed farther apart. Measuring this acceleration requires tracking how voids evolve over time. By comparing voids at different distances, which correspond to different cosmic epochs, astronomers can see how void properties change. Nearby voids like Boötes are mature, fully developed after billions of years of expansion. Distant voids, seen as they were in the younger universe, are smaller and less empty. This evolution matches predictions based on dark energy. The integrated Sachs-Wolf effect, mentioned earlier, is a direct signature of dark energy's influence on voids. As photons from the cosmic microwave background pass through an expanding void, they lose a small amount of energy. This happens because the gravitational potential of the void changes while the photons are inside it, a consequence of accelerated expansion driven by dark energy. Detecting this effect confirms that voids are shaped by dark energy. The interplay between dark matter and dark energy defines the void structure. Dark matter sets the initial conditions, determining where underdensities form. Gravity, mediated by dark matter, pulls matter out of voids and into filaments. Dark energy then accelerates the expansion, stretching voids larger and preventing matter from falling back in. The Boötes Void is a product of both forces working in tandem. This raises profound questions. What is dark matter made of? Leading candidates include weakly interacting massive particles, or WIMPs, and axions, hypothetical particles predicted by certain extensions of the standard model of particle physics. If dark matter has additional properties, such as self-interaction, it could change how voids form and evolve. The Boötes Void, as an extreme case, could help test these possibilities. What is dark energy? The simplest explanation is a cosmological constant, a uniform energy density filling all of space. But dark energy could also be a dynamic field that varies over time or across space, known as quintessence. Different models of dark energy predict slightly different behaviors for voids. By measuring void properties with precision, astronomers can distinguish between these models. The mystery deepens when we consider that we can only infer dark matter and dark energy from their effects. We cannot see them directly, cannot touch them, cannot isolate them in laboratories. They are known only through their influence on visible matter and on the expansion of space. The Boötes Void is shaped by forces we do not fully understand, structured by substances we cannot observe. Yet this is not a failure of science, but a frontier. The void becomes a laboratory for testing ideas about dark matter and dark energy. Its size, its shape, its emptiness, and its evolution all carry information about these invisible components. Every measurement refines our understanding, constraining possibilities and guiding theory. As you let this settle, imagine the Boötes Void as a stage where dark matter and dark energy perform their invisible choreography. Dark matter provides the scaffolding, the framework on which structure rests. Dark energy drives the expansion, pushing galaxies apart and stretching voids larger. Together, they shape the void, making it what it is. The deeper mystery is not just that the void exists, but that it is sculpted by forces we are only beginning to comprehend. There are moments in science when a discovery does not just add to knowledge, but transforms how we see the world. The Boötes Void was one such moment. Its discovery marked a paradigm shift in cosmology, changing how astronomers thought about the large-scale structure of the universe and revealing that emptiness was as important as presence. Before the void was discovered, cosmologists understood that galaxies clustered together. They knew about groups, clusters, and even superclusters, vast concentrations of galaxies bound by gravity. The focus was naturally on these dense regions, where galaxies gathered and interacted. The spaces between were thought of as gaps, background features that did not warrant much attention. The Boötes Void changed that perspective. It showed that the gaps were not just empty space, but structures in their own right. Voids had sizes, shapes, and properties that could be measured and studied. They were not passive backdrops, but active participants in cosmic evolution. The paradigm shifted from seeing the universe as a collection of galaxy clusters to seeing it as a cosmic web, where voids and filaments were equally fundamental. This shift required rethinking how structure forms. The traditional picture focused on how over-dense regions collapsed under gravity, pulling matter together to form galaxies and clusters. But voids revealed the flip side of that process. Under dense regions, expanded, losing matter to their surroundings. The same physics that built clusters also carved out voids. Structure formation was not just about concentration, but also about evacuation. The paradigm shift also involved recognizing that the universe is fundamentally inhomogeneous on large scales. Before detailed surveys, there was an assumption that if you averaged over large enough volumes, the universe would appear uniform. The cosmic microwave background, with its tiny fluctuations, seemed to support this. But the Boötes Void and other large structures showed that inhomogeneity persisted even on scales of hundreds of millions of light years. This had implications for how cosmologists interpreted observations. If the universe was not uniform on large scales, then measurements made from our particular location might not represent the cosmic average. This became especially relevant for debates about the expansion rate and whether our local region was typical or atypical. The void reminded everyone that position matters, that the universe looks different from different vantage points. The discovery also shifted attention to the role of dark energy. When the Boötes Void was first found in the early 1980s, dark energy had not yet been discovered. But as evidence for cosmic acceleration emerged in the late 1990s, voids like Boötes became important testing grounds. Voids are sensitive to dark energy because they expand more freely than dense regions. The paradigm shift included recognizing that voids could probe the nature of dark energy. Another aspect of the shift was methodological. Mapping voids required three-dimensional surveys, not just images of the sky. Redshift measurements transformed astronomy from a two-dimensional to a three-dimensional science. The Boötes Void was one of the first dramatic examples of what this new approach could reveal. It demonstrated the power of systematic surveys and inspired larger, more ambitious projects. The shift also involved a change in language. Astronomers began talking about the cosmic web, a term that captured the interconnected nature of filaments, walls, and voids. The universe was not a random scattering of galaxies, but a structured network. Voids were the holes in the web, essential to its architecture. Without them, the filaments would not stand out. Without filaments, the voids would not be defined. Presence and absence were two sides of the same coin. Theoretical cosmology underwent a parallel shift. Simulations that once focused only on where galaxies formed began including predictions for where they did not form. Void statistics became a tool for testing models, alongside traditional measures like the galaxy correlation function. The paradigm expanded to include emptiness as data. The shift also touched on philosophical questions about what it means to study the universe. Science had traditionally focused on objects, on things that exist. The Boötes Void forced a reckoning with the idea that absence could be studied just as rigorously. Nothingness, or near-nothingness, became a subject worthy of serious inquiry. The void was not a failure of observation, but a feature to be explained. This transformation was not instantaneous. It took years for the implications to fully sink in, for the community to adjust its thinking. Early papers on the void emphasized its size and strangeness. Later papers explored its dynamics, its role in testing cosmological models, and its place in the broader cosmic web. The paradigm shifted gradually as more voids were discovered and as their properties were catalogued and compared. The Boötes Void also inspired a generation of astronomers to look for other extreme structures. If one void this large existed, might there be others? The search led to the discovery of additional supervoids, each contributing to the growing understanding that the universe contains structures at the edge of what theory predicted. The paradigm became one of expecting the unexpected, of recognizing that the universe could surprise. One of the most profound aspects of the shift was the recognition that voids connect the smallest scales to the largest. The tiny quantum fluctuations during inflation, less than 1 part in 100,000, grew into structures spanning hundreds of millions of light years. The Boötes Void was a direct link between the earliest moments of the universe and the present day. It showed that the cosmos has memory, that initial conditions matter even after billions of years. The shift also affected how cosmologists thought about the future. If voids are expanding faster than the universe as a whole, driven by dark energy, then in the distant future, voids will dominate. Galaxies will become increasingly isolated, surrounded by vast emptiness. The Boötes Void is a preview of that future, a glimpse of what the universe will become when expansion has carried everything far apart. As you rest with this idea, imagine the moment when astronomers realized that the universe was not just about galaxies clustering, but also about the spaces between them. Picture the shift in perspective, the recognition that emptiness had structure and meaning. The Boötes Void was not just a hole in the map. It was a doorway to a new way of seeing the cosmos, one where voids and filaments together told the story of how matter organized itself over cosmic time. The paradigm shift is ongoing. Each new survey, each new measurement, refines the picture. But the fundamental insight remains. The universe is a web, and the Boötes Void is one of its most dramatic features. A vast cavity that helped transform cosmology from a science of things to a science of structures, where absence is as revealing as presence. When the Boötes Void was announced, the immediate ripple through the scientific community was one of intense curiosity followed by rapid action. The discovery raised so many questions that astronomers immediately began planning new observations. Theorists started refining their models, and the void became a focal point for research programs around the world. The first ripple was observational. If a void this large existed in Boötes, might there be others elsewhere in the sky? Astronomers began examining their data more carefully, looking for similar underdensities in other regions. Within a few years, additional voids were discovered, though none quite as large as Boötes. This confirmed that voids were not unique anomalies but a common feature of the cosmic web. The discovery also prompted more detailed follow-up observations of the Boötes region itself. Deeper surveys were conducted to search for faint galaxies that might have been missed in the initial work. Radio telescopes scanned for neutral hydrogen, mapping the gas content of the void. Infrared observations looked for dusty star-forming galaxies that might be invisible in optical light. Each new observation added detail to the picture. Theorists responded with simulations. The immediate question was whether the standard model of cosmology could produce voids as large as Boötes. Early simulations suggested yes, but the statistics were uncertain. More sophisticated models were developed, with higher resolution and larger volumes, to better predict the frequency and properties of supervoids. These simulations became benchmarks against which observations could be tested. The void also influenced how cosmologists thought about surveys. It became clear that mapping the universe required not just identifying where galaxies were, but also where they were not. Survey strategies shifted to ensure complete coverage, avoiding gaps that might hide voids. The Boötes Void demonstrated that absence was data, and that comprehensive three-dimensional mapping was essential. There was also an immediate impact on the interpretation of galaxy clustering. Measurements of how galaxies cluster on different scales had to account for voids. The presence of large underdensities affects statistical measures like the two-point correlation function, which describes how likely galaxies are to be found at various separations. Voids contribute to the large-scale tail of this function, and ignoring them would lead to incomplete models. The discovery rippled into adjacent fields. Cosmologists studying the cosmic microwave background realized that voids could leave imprints on the ancient radiation through the integrated Sachs-Wolf effect. This connection between structure and the background became an active area of research, with scientists looking for correlations between void positions and temperature fluctuations in the microwave sky. The Boötes Void also affected debates about the nature of dark matter. If voids were regions where dark matter was sparse, then studying them could reveal properties of dark matter that were hard to access in dense environments. For example, if dark matter particles could self-interact, it might change how voids form and evolve. The void became a laboratory for testing dark matter physics. Public interest was another ripple. News of a giant hole in the universe captured imaginations. Articles appeared in popular science magazines explaining the void in accessible terms. The phrase, largest hole in the universe, became associated with Boötes, though astronomers cautioned that it was not a hole in the literal sense, but an underdensity. Still, the imagery was powerful and helped bring cosmology to a wider audience. Within the astronomical community, the void inspired new collaborations. Researchers from different institutions pooled their data, shared telescope time, and worked together to map the structure in greater detail. The Boötes Void became a common reference point, a structure that everyone could study and compare results on. It fostered a sense of shared purpose. The discovery also highlighted the importance of systematic surveys over targeted observations. The void had been found not by looking for something specific, but by mapping a region comprehensively. This lesson carried forward into the design of future surveys, which aimed for completeness and uniformity. The Sloan Digital Sky Survey, launched in the late 1990s, was influenced by this philosophy and went on to discover thousands of voids. Another immediate effect was on the training of young astronomers. Graduate students in the 1980s and 90s grew up with the Boötes Void as a known feature of the cosmos. It became a standard example in textbooks and courses, illustrating concepts like structure formation, gravitational instability, and the cosmic web. A generation of scientists internalized the idea that voids were fundamental. The void also prompted questions about our own location. If voids this large existed, could we be living in or near one? This question became more pointed with the later proposal of the KBC void, a possible underdensity on even larger scales that might encompass the Milky Way. The Boötes Void made such ideas seem less far-fetched, showing that extreme structures were real. Funding agencies took notice. Proposals for telescopes and surveys often highlighted the study of large-scale structure, including voids, as a priority. The Boötes Void had demonstrated that there were important discoveries to be made by mapping the universe on the largest scales, and resources flowed toward projects that could do that mapping. There was also a ripple in how cosmologists communicated their findings. The void was unusual enough to attract attention, and astronomers learned to frame their research in ways that conveyed both the science and the wonder. The balance between technical accuracy and public engagement became a model for how to discuss abstract cosmological concepts. The immediate ripple also included skepticism. Some scientists questioned whether the void was as extreme as claimed, whether observational biases had exaggerated its emptiness. These challenges were healthy, prompting careful re-examination of the data and leading to more robust conclusions. The back and forth strengthened the overall understanding. As you consider these ripples, imagine the energy that flowed through the community after the discovery. Conference halls buzzing with discussion, observatories scheduling follow-up observations, theorists running new simulations. The Boötes Void had opened a door, and astronomers rushed through it, eager to explore what lay beyond. The immediate ripple was one of action, of momentum, of a field energized by a new puzzle to solve. The discovery of the Boötes Void did not just affect the immediate present. Its echoes have reverberated through decades of cosmological research, shaping how scientists think about structure, how they design observations, and how they interpret the universe. The void's influence extends from the past into the future, connecting different eras of discovery. Looking backward, the void cast new light on earlier observations. Before its discovery, astronomers had noticed irregularities in the distribution of galaxies, but these were often attributed to noise or incomplete sampling. The Boötes Void showed that such irregularities could be real features, not artifacts. It prompted a re-examination of older surveys, revealing that hints of voids had been there all along, waiting to be recognized. The void also connected to theoretical work from earlier decades. In the 1970s, cosmologists had begun developing models of structure formation based on gravitational instability. These models predicted that over dense regions would collapse and under dense regions would expand. The Boötes Void was confirmation that the second half of that prediction was correct. It validated theoretical insights that had been largely untested. Moving forward in time, the void influenced the design of major surveys. When astronomers planned the Sloan Digital Sky Survey, they knew that capturing large-scale structure, including voids, was essential. The survey's strategy of covering large areas of sky with uniform depth was shaped in part by lessons from Boötes. The result was a database of thousands of voids, transforming void cosmology from the study of a few examples to a statistical science. The void's echoes also reached into the study of dark energy. When cosmic acceleration was discovered in the late 1990s, voids became important probes of dark energy's properties. The Boötes Void, already well studied, provided a benchmark. Its size and emptiness could be compared to predictions based on different models of dark energy, helping distinguish between a cosmological constant and more exotic alternatives. Echoes of the void appear in studies of the cosmic microwave background. As satellites mapped the ancient radiation with increasing precision, cosmologists looked for correlations with the positions of voids. The integrated Sachs-Wolf effect, a subtle signal caused by photons passing through voids, was predicted and eventually detected. The Boötes Void contributed to this detection, its large size making it one of the more significant contributors to the stack signal. The void also influenced how cosmologists think about the universe's fate. If dark energy continues to drive accelerated expansion, voids will grow ever larger, eventually dominating the volume of the universe. The Boötes Void is a preview of this future, a glimpse of what the cosmos will look like when galaxies are scattered so far apart that each exists in profound isolation. The echoes of the void extend not just through past and present, but into the distant future. In the realm of theory, the void has echoed through discussions of alternative cosmologies. Some researchers have proposed that the apparent acceleration of the universe could be explained by inhomogeneities rather than dark energy. In these models, voids play a central role. While these ideas have not displaced the standard model, they keep the conversation open, reminding everyone that voids are sensitive tests of fundamental physics. The Boötes Void has also echoed through popular culture. Its image as the largest hole in the universe has appeared in documentaries, articles, and even works of fiction. It has become a symbol of the mysterious and the vast, a reminder that the universe contains features beyond everyday comprehension. This cultural echo has helped sustain public interest in cosmology. Within the scientific community, the void echoes through citation networks. Papers on large-scale structure, on voids, on dark energy, and on structure formation regularly reference the original discovery. The Boötes Void is a touchstone, a standard example that connects different threads of research. Its influence can be traced through the literature, linking studies across decades. The void's discovery also echoed into the training of scientists. Generations of graduate students have learned about the Boötes Void in their courses, using it to understand concepts like redshift surveys, density contrasts, and gravitational instability. These students have gone on to conduct their own research, some of them discovering new voids, others developing new theoretical models. The echo continues through the careers they build. There are also personal echoes. The astronomers who discovered the void, Robert Kirshner and his colleagues, went on to distinguished careers, contributing to other major discoveries including the detection of cosmic acceleration. The skills and insights gained from studying the void carried forward into their later work. The discovery shaped not just the field, but the individuals who made it. The void has echoed through technological development. The need to map large-scale structure drove improvements in telescope design, detector sensitivity, and data processing. Techniques developed to study the Boötes Void were refined and applied to other problems. The echo of the discovery is embedded in the tools astronomers use today. Looking toward the future, the echoes will continue. Upcoming surveys with next-generation telescopes will map voids with unprecedented detail. The Boötes Void will remain a reference point, a structure against which new discoveries are compared. Its echoes will shape research for years to come, influencing how cosmologists think about structure, how they test models, and how they interpret observations. There is also an echo in the way we think about scale. The Boötes Void, by being so large, forces us to confront the vastness of the universe. It reminds us that structures exist on scales far beyond human experience, that the cosmos operates on timescales and distance scales that dwarf our lives. This humbling echo affects not just science, but philosophy, our sense of place in the universe. The void's echoes also connect to the deepest questions. What is the nature of space? What is the origin of structure? What is the fate of the cosmos? The Boötes Void, as an extreme feature, touches on all of these. Its echoes reverberate through discussions of initial conditions, of dark matter and dark energy, of expansion and evolution. It is a link between the observable and the fundamental. As you rest with these echoes, imagine them spreading outward like ripples on a pond. The discovery of the Boötes Void was a single moment, but its influence extends in all directions through time. It changed the past by reinterpreting earlier observations, shaped the present by guiding research, and will affect the future by setting benchmarks and inspiring questions. The echoes of the void are still sounding, and they will continue long after we are gone. Behind every great discovery in astronomy are people, individuals driven by curiosity, patience, and the desire to understand. The Boötes Void was no exception. Its discovery and continued study have been shaped by dreamers, scientists who devoted years to mapping the invisible, measuring the absent, and making sense of emptiness. Robert Kirshner was one of the central figures in the void's discovery. Born in 1949, Kirshner became interested in astronomy as a young man, drawn to the mysteries of the cosmos. By the late 1970s, he was working on redshift surveys, mapping the three-dimensional distribution of galaxies. His approach was methodical and careful, measuring galaxy after galaxy, building maps one data point at a time. Kirshner was not working alone. Augustus Oehmler, Paul Schechter, and Stephen Schechtman were his collaborators, each bringing their own expertise to the project. Together, they formed a team that combined observational skill with theoretical insight. They understood that mapping galaxies required patience, that the universe would reveal its structure only to those willing to look carefully. The work was demanding. Nights at the telescope were long and often frustrating. Equipment failed, weather interfered, and the data were sometimes ambiguous. But the team persisted, driven by the belief that systematic surveys would uncover patterns invisible to casual observation. They were right. When they plotted their measurements, the Boötes Void emerged, a vast emptiness that no one had expected. Kirshner later described the discovery with a mix of excitement and caution. He knew they had found something important, but he also knew that extraordinary claims required extraordinary evidence. The team checked and rechecked their data, looking for errors or biases that might explain the gap. When none were found, they published their results, opening the void to scrutiny from the wider community. The discovery changed Kirshner's career. He became known not just as an observer of galaxies, but as someone who had revealed one of the universe's most extreme structures. Later, he would go on to contribute to another major discovery, the acceleration of cosmic expansion, work that earned a Nobel Prize for his colleagues. But the Boötes Void remained a defining moment, a reminder that careful observation could yield profound surprises. Augustus Oehmler brought a different perspective. He was interested in how galaxies evolved, how their properties changed depending on their environment. The void provided a natural experiment, a place where galaxies lived in isolation, free from the disruptive influences common in clusters. Oehmler saw the void not just as an empty region, but as a laboratory for understanding galaxy evolution. Paul Schechter contributed theoretical insights. He worked on models of how galaxies form and how their luminosities are distributed. The void challenged those models, pushing them to explain why certain regions contain so few galaxies. Schechter's work helped bridge observation and theory, showing how the void fit into the larger picture of structure formation. Stephen Schechtman was the observational specialist, skilled at coaxing data from telescopes, at ensuring that measurements were accurate and reliable. His technical expertise was essential to the discovery. Without careful calibration and precise redshift measurements, the void might have remained hidden, lost in the noise of imperfect data. These four dreamers were part of a larger community, a network of astronomers working at observatories around the world. Mount Wilson, Kitt Peak, Las Campanas. Each of these sites contributed to the mapping effort. The telescopes were tools, but the dreamers were the ones who knew how to use them, who understood what questions to ask and how to interpret the answers. There were others as well. Graduate students who spent long nights at telescopes, taking spectra, reducing data, checking calculations. Technicians who maintained the instruments, ensuring they worked reliably. Theorists who ran simulations, testing whether models could reproduce what observers saw. The discovery of the Boötes Void was a collective effort, built on the contributions of many. What united these dreamers was a willingness to look at the universe without preconceptions. They did not set out to find a void. They set out to map galaxies, to see what patterns emerged. When the data revealed emptiness, they did not dismiss it as an error. They followed where the evidence led, even when it pointed to something unexpected. This openness to surprise is a hallmark of great science. Many discoveries happen not because someone was looking for a specific thing, but because someone was looking carefully at everything. The Boötes Void was found by dreamers who mapped the sky systematically, who trusted their measurements, and who were willing to report what they saw, even when it challenged assumptions. The dreamers also understood the importance of patience. Mapping the universe is not quick work. Each galaxy requires time, each measurement must be checked, each conclusion must be verified. The Boötes Void was not discovered in a single night, but over months and years of accumulated observations. The dreamers knew that understanding comes slowly, that the cosmos reveals itself to those who wait. There is also a human dimension to these stories. Kirschner, Oehmler, Schechter, and Schechtman were not just scientists, but people with lives, families, and interests beyond astronomy. They balanced the demands of research with the demands of living. They experienced the frustrations of failed observations and the joys of successful ones. They collaborated, disagreed, and supported one another. The discovery of the void was a professional achievement, but it was also a personal one, a shared experience that bound them together. Later generations of dreamers have continued the work. Astronomers have mapped thousands of voids, refining the picture of the cosmic web. Each void discovered adds to the catalogue. Each measurement improves the models. The Boötes Void remains the most famous, but it is part of a larger story, one that continues to unfold. These later dreamers use more advanced tools, automated surveys, digital detectors, powerful computers. But the spirit is the same. They are driven by curiosity, by the desire to map the universe, to understand its structure, to see patterns in the data. The Boötes Void inspires them, a reminder that careful observation can reveal the extraordinary. As you let this settle, imagine those dreamers at their telescopes, night after night, measuring the light from distant galaxies. Picture the moment when the void first appeared in their plots, a gap where galaxies should be. Imagine the discussions, the debates, the careful checking of data. The Boötes Void is not just a structure in space, but a human achievement, the result of dedication, patience, and the willingness to dream about what the universe might contain. Science progresses not through unchallenged acceptance, but through rigorous testing, skepticism, and debate. When the Boötes Void was first announced, it immediately became the subject of scrutiny. Some astronomers questioned the measurements, others doubted the interpretation. The battle for truth was fought not with hostility, but with data, with careful analysis, and with the insistence that extraordinary claims require extraordinary evidence. The first line of questioning focused on the observations themselves. Were the redshifts accurate? Redshift measurements depend on identifying spectral lines and measuring their wavelengths with precision. If the measurements were systematically off, the void might be an artifact, a mirage, created by errors. Critics examined the data carefully, checking calibrations, looking for systematic biases. The team that discovered the void welcomed this scrutiny. They provided their data, explained their methods, and invited independent verification. Other astronomers conducted their own observations of the Boötes region, measuring redshifts for galaxies in and around the void. These independent measurements confirmed the original findings. The void was real, not a product of faulty data. Another line of questioning involved completeness. Perhaps the void only appeared empty because faint galaxies had been missed. Early surveys had detection limits, below which galaxies were too dim to be seen. If many faint galaxies existed in the void, it might not be as empty as claimed. This was a reasonable concern, and it prompted deeper observations. Follow-up surveys with more sensitive instruments searched for faint galaxies in the void. Radio telescopes looked for neutral hydrogen, which could reveal low-mass galaxies invisible in optical light. Infrared observations searched for dusty systems, hidden from view. These deeper surveys found a few additional galaxies, but not enough to significantly change the picture. The void remained profoundly underdense. There was also debate about how to define the void's boundaries. Different algorithms for identifying voids in galaxy surveys could produce different results. Some methods emphasized sphericity. Others allowed for irregular shapes. Some set strict density thresholds. Others used more flexible criteria. The Boötes Void was robust across most methods, but the exact size and depth varied slightly depending on the definition used. This debate was healthy. It forced researchers to be precise about what they meant by a void, to develop consistent definitions that could be applied across different surveys. The battle was not about whether the void existed, but about how best to characterize it. The outcome was a more rigorous framework for studying voids in general. Theorists joined the debate by questioning whether the standard model could produce such a large void. Early simulations were limited by computational power, and it was not clear whether they could reproduce structures as extreme as Boötes. Some researchers suggested that if the void could not be explained by standard cosmology, it might indicate new physics, perhaps related to the initial conditions or to the properties of dark matter. This challenge motivated better simulations. As computers became more powerful, cosmologists ran larger, higher resolution models. These simulations showed that voids as large as Boötes could form, though rarely. The probability was low, but not impossibly so. The void fit within the tail of the expected distribution. The battle shifted from whether the void was possible to whether its existence constrained cosmological parameters. There were also debates about the implications of the void. Some saw it as a critical test of structure formation theories, a feature that could distinguish between competing models. Others viewed it as an interesting outlier, but not fundamentally challenging. These differing perspectives reflected broader debates about how to interpret extreme structures. Were they windows into new physics, or simply rare but expected outcomes? The battle for truth also involved comparing the Boötes Void to other voids discovered later. If Boötes were unique, it might suggest something unusual about that region. But as more voids were found, including other large ones, it became clear that Boötes was exceptional but not alone. This comparative approach helped establish that voids were a general feature of the cosmic web. With Boötes at the extreme end of the spectrum, One of the most important aspects of the battle was the insistence on reproducibility. Science requires that results be confirmed independently, not just accepted on authority. The Boötes Void passed this test. Multiple teams, using different telescopes and different techniques, measured the same under density. The consistency across independent observations was compelling evidence that the void was real. There were moments of tension. Papers were published challenging aspects of the void's interpretation, and responses were written defending the original findings. Conferences featured debates where scientists presented conflicting views, but these tensions were productive, driving everyone to sharpen their arguments, improve their data, and think more carefully about what the void meant. The battle also extended to public communication. When news of the void reached the media, headlines sometimes exaggerated its strangeness, calling it a hole in space or a mysterious absence. Scientists had to balance excitement with accuracy, explaining that the void was an underdensity, not a literal hole, and that it fit within the framework of cosmology, even if it was extreme. Over time, the battle settled into consensus. The Boötes Void was real, it was large, and it was consistent with the standard model, though at the edge of expectations. The skepticism had been warranted, but the evidence was strong. The battle for truth had been won not by any single argument, but by the accumulation of consistent observations and the careful refinement of theory. This process is how science works at its best. Claims are tested, data are scrutinized, and conclusions are reached through evidence, not authority. The Boötes Void emerged from this process stronger, its reality confirmed by multiple lines of evidence. The battle was not a failure of cooperation, but a demonstration of science's self-correcting nature. As you consider this, imagine the conferences, the papers, the back and forth of argument and evidence. Picture scientists presenting data, challenging interpretations, defending conclusions. The battle for truth was not a conflict, but a conversation, one that ultimately strengthened understanding. The Boötes Void stands today as a confirmed feature of the cosmos, tested and verified, a structure whose reality has survived the scrutiny of skeptics. The discovery of the Boötes Void did more than add a feature to the cosmic map. It created a new awareness, a shift in how we understand our place in the universe. This awareness touches on scale, on structure, on the nature of emptiness, and on the limits of what we can know. It is an awareness that humbles and inspires in equal measure. The first dimension of this awareness is scale. The Boötes Void stretches 330 million light-years across, a distance so vast that it challenges comprehension. To travel across it at the speed of light would take longer than life has existed on Earth, longer than the dinosaurs roamed, longer than continents have drifted. The void is not just large in human terms, but large on cosmic terms, comparable to the largest structures in the universe. This scale forces a reckoning with our own smallness. The entire Earth fits into a point invisible on any map of the void. The solar system is a speck. Even the Milky Way, with its hundreds of billions of stars, would be a tiny marker if placed inside Boötes. The void makes us aware that the universe operates on scales far beyond our immediate experience, that there are structures so immense we can barely hold them in our minds. But the awareness is not just about size, it is also about structure. The Boötes Void revealed that the universe is not uniformly filled with galaxies, but organized into a web of filaments, walls, and voids. This web is not random, but shaped by the physics of gravity, by the initial conditions of the Big Bang, and by billions of years of evolution. The awareness is that the cosmos has architecture, that absence and presence together define its form. This awareness changes how we see the night sky. When we look up, we see stars, galaxies, light, but we are also looking at the edges of voids, the boundaries of emptiness that stretch beyond our view. The sky is not just filled with objects, but structured by the spaces between them. The Boötes Void is invisible to our eyes, but it is there, shaping the distribution of light, influencing the paths of photons, and defining the cosmic landscape. The void also creates awareness of time. It did not always exist in its current form. Billions of years ago, The region that became Boötes was only slightly less dense than average, a small fluctuation barely perceptible in the early universe. Over time, that fluctuation grew, amplified by gravity, stretched by expansion, until it became the vast cavity we observe today. The void is a record of cosmic history, a structure that tells the story of how the universe evolved. This awareness connects us to the earliest moments. The seed of the Boötes Void was planted during cosmic inflation, when quantum fluctuations were stretched to macroscopic scales. Those fluctuations, imprinted in the cosmic microwave background, are the ancestors of all structure. The void is a descendant of the Big Bang, a link between the first fraction of a second and the present day. To study the void is to study origins. There is also awareness of what we do not know. The void is shaped by dark matter and dark energy, substances that make up most of the universe but remain mysterious. We cannot see them directly, cannot touch them, cannot isolate them. We know they exist only through their effects. The Boötes Void is a reminder that the universe is mostly invisible, that what we observe is only a small fraction of what exists. This awareness is humbling. It reveals the limits of human knowledge, the gaps in our understanding. But it is also exciting. It shows that there are still mysteries to solve, questions to answer, discoveries to make. The void is both a known feature and an unsolved puzzle, a structure we can map but not fully explain. Awareness is that science is incomplete, that the journey toward understanding is ongoing. The void also creates awareness of isolation. The few galaxies inside Boötes exist in near solitude, separated from their neighbours by vast distances. They are survivors, systems that formed in conditions of profound scarcity. Their isolation shapes their evolution, making them different from galaxies in denser regions. The awareness is that environment matters, that where a galaxy lives determines how it grows. This awareness extends to ourselves. We live in a relatively dense part of the universe, in a galaxy surrounded by others, in a region where matter is concentrated. But the Boötes Void reminds us that most of the universe is not like our neighbourhood. Most of the cosmos is empty, or nearly so. Our experience is not typical. The awareness is that we are fortunate, living in a pocket of abundance in a universe dominated by scarcity. There is also awareness of the future. The void is expanding, driven by dark energy, growing larger and emptier with time. In the distant future, billions of years from now, the universe may be filled with voids like Boötes, with galaxies scattered so far apart that each exists in isolation. The void is a preview of that future, a glimpse of what the cosmos will become when expansion has carried everything beyond reach. This awareness is bittersweet. It shows that the universe is not eternal in its current form, that the structures we see are temporary, that even the cosmic web will one day dissolve. But it also shows that the universe is dynamic, evolving, always changing. The awareness is that nothing lasts forever, but that each moment is part of a larger story. A cosmic narrative that began with the Big Bang and will continue for trillions of years. The Boötes Void also creates awareness of our capacity to understand. Despite its size, despite its strangeness, the void can be explained. We have theories that account for its formation, simulations that reproduce its properties, and observations that test our models. The awareness is that human minds, though small and brief, can comprehend structures that dwarf us in scale and time. We are part of the universe, and we can understand it. As you rest with this awareness, imagine the Boötes Void not just as a structure in space, but as a mirror reflecting our place in the cosmos. It shows us our smallness, but also our connection. It reveals our ignorance, but also our capability. The void is a teacher, offering lessons about scale, structure, time, and mystery. The awareness it creates is profound, a shift in perspective that changes how we see the universe and ourselves. After all the observations, all the measurements, all the theories, there remains a question that goes to the heart of what the Boötes Void reveals. What is the deepest truth hidden in this vast emptiness? What does it tell us about the nature of reality, about the universe we inhabit, and about the forces that shape everything? The deepest truth may be this: The universe is not built from objects alone, but from relationships between presence and absence. The Boötes Void is not just a whole, but a structure defined by what surrounds it. The filaments and walls that border the void gain their meaning from the emptiness they contain. Without voids, the cosmic web would not exist. Without absence, presence would have no contrast. This truth overturns a basic assumption. We think of reality as things, as matter, as objects that exist. But the void shows that absence is equally real, equally structural. The universe is not just about where matter is, but also about where it is not. The deepest truth is that nothingness is not the opposite of existence, but a part of it, woven into the fabric of the cosmos. This truth extends to the physics of structure formation. The same processes that build galaxies and clusters also create voids. Gravity pulls matter into over-dense regions, and in doing so, it evacuates under dense regions. The two processes are inseparable. The void is not a failure of galaxy formation, but its complement. The deepest truth is that creation and evacuation are two sides of the same coin. The Boötes Void also reveals a truth about time. It did not spring into existence fully formed. It grew, slowly, over billions of years, from a tiny fluctuation in the early universe. The void is a process, not a thing, an unfolding that continues even now. The deepest truth is that the universe is not static, but dynamic, that structures are not fixed, but evolving, and that time is written into everything we see. This truth connects to the initial conditions of the cosmos. The fluctuations that seeded the void were quantum in origin, arising from the uncertainty inherent in fields during inflation. The void is a macroscopic manifestation of quantum processes, a bridge between the smallest and largest scales. The deepest truth is that the universe carries memory, that the earliest moments determine the present, and that quantum randomness shapes cosmic destiny. The void also reveals a truth about dark matter and dark energy. These invisible substances dominate the universe, making up 95% of its content. The void is shaped by their interplay, carved by dark matter's gravity, stretched by dark energy's push. The deepest truth is that the universe is mostly hidden, that what we see is only a small fraction of what exists, and that the forces shaping reality are largely invisible to us. This truth is humbling. It shows the limits of perception, the gaps in understanding, but it also shows the power of inference. We cannot see dark matter or dark energy directly, but we can map their effects, measure their influence, and test their properties. The void is a tool for probing the invisible, a lens through which the hidden universe reveals itself. The deepest truth is that science can reach beyond the visible, that knowledge is not limited to what we can touch or see. The Boötes Void also reveals a truth about scale. The universe operates on many levels, from quantum fluctuations to cosmic voids, each connected to the others. The void is not separate from galaxies, or from stars, or from atoms. It is part of a continuum, a structure that links the smallest scales to the largest. The deepest truth is that the universe is unified, that all scales are connected, and that understanding any part requires understanding the whole. There is also a truth about rarity. The Boötes Void is exceptional, sitting at the extreme end of the distribution of structures. It is rare, but not impossible, a statistical outlier that tests the limits of theory. The deepest truth is that the universe includes extremes, that probability allows for the unlikely, and that rare events are part of the natural order. The void does not break the rules, it stretches them, showing what is possible within the framework of physics. The void reveals a truth about prediction. Cosmologists predicted that voids should exist before any were discovered. The theory came first, the observation second. The Boötes Void confirmed those predictions, validating decades of theoretical work. The deepest truth is that mathematics can describe reality, that equations can predict structures, and that the universe follows laws we can understand. But the void also reveals limits to prediction. Its exact size, its precise location, the number of galaxies inside, These details are the outcomes of random fluctuations, not deterministic laws. The deepest truth is that the universe is partly predictable and partly random, that laws set the framework, but chance fills in the details. The void is both explained and unique, both typical and exceptional. There is a truth about impermanence. The void is expanding, growing larger and emptier with time. It is not eternal, it had a beginning, and it has a future. In trillions of years, it may dominate the observable universe, as all galaxies recede beyond horizons. The deepest truth is that nothing lasts forever, that even the most solid structures are temporary, and that change is the only constant. The void is a reminder that the universe is not fixed, but flowing, always becoming. The Boötes Void also reveals a truth about knowledge itself. We have mapped it, measured it, and explained it, yet it remains mysterious. We understand how it formed, but we still wonder at its size. We know the physics, but we still feel the awe. The deepest truth is that understanding and wonder are not opposites, that science does not erase mystery, but transforms it. The void is both known and unknowable, both explained and astonishing. Finally, the void reveals a truth about humanity. We are small, brief, and located in one tiny corner of the cosmos. Yet we have discovered a structure that spans hundreds of millions of light years, traced its origins to the earliest moments of time, and connected it to the ultimate fate of the universe. The deepest truth is that consciousness, the ability to wonder and understand, is one of the universe's most remarkable achievements. We are part of the cosmos, and we can comprehend it. As you let this settle, imagine the Boötes Void as a window into the deepest truths. It is not just a hole in space, but a revelation about structure, time, matter, and meaning. The truths it reveals are layered, each one opening onto the next, connecting the visible to the invisible, the present to the past and future, the small to the vast. The void is a teacher, and its lessons are profound. When the observations are complete, when the data are analysed, when the theories are tested, there comes a moment to pause and ask, what does it all mean? The Boötes Void is a scientific fact, confirmed by evidence and understood through physics. But it is also something more, a structure that invites reflection on deeper questions about existence, purpose, and our place in the cosmos. One meaning of the void is that the universe has a story. It is not eternal and unchanging, but evolving, with a beginning, a middle, and perhaps an end. The Boötes Void is a chapter in that story, a structure that arose from tiny fluctuations in the early universe, and that will continue to grow as expansion accelerates. To ponder the void is to see ourselves as part of a narrative, one that began nearly 14 billion years ago and will continue for trillions more. Another meaning is that we are not separate from this story. The atoms in our bodies were forged in stars that lived and died long before the Earth existed. The void shaped the distribution of those stars, influenced where galaxies formed, and indirectly determined the conditions that allowed life to arise. We are connected to the void, not by proximity, but by the shared history of the cosmos. To ponder the void is to recognize that connection. The void also raises questions about purpose. Does the universe have a purpose? Does the void serve some goal? Science does not answer these questions because science deals with how, not why. It describes the mechanisms, the laws, the patterns, but it does not tell us whether there is intention behind them. Some find purpose in the beauty and order of the cosmos, in the fact that it is knowable. Others accept that purpose may be absent, that the universe simply is, without needing a reason. What the void does reveal is that if there is purpose, it is not centered on us. The cosmos does not revolve around humanity. It existed for billions of years before we appeared, and it will continue for trillions more after we are gone. The void, stretching across hundreds of millions of light years, utterly indifferent to our existence, makes this clear. Our significance, if we have any, is not given by the universe. It is something we create through our actions, our relationships, our quest for understanding. To ponder the void is also to confront the question of meaning in the face of vastness. The The scale of the void can feel overwhelming, as if our lives are too small to matter. But scale is not the same as significance. Meaning is not measured in light years or trillions of years. It is found in moments, in connections, in the choices we make and the lives we touch. The void does not diminish us. It provides context, a backdrop against which human life unfolds. There is also the question of fate. If the void is expanding, if dark energy continues to drive acceleration, what does that imply for the future? The universe will grow colder, emptier, darker. Stars will exhaust their fuel, galaxies will drift beyond reach, and eventually, even black holes will evaporate. The void is a preview of that future, a glimpse of what the cosmos will become. This vision is stark, but it is also honest. To ponder it is to accept that nothing lasts forever, that even the universe has a lifespan. Yet this, fate is so distant, measured in trillions of years, that it does not touch the immediate concerns of life. The stars will shine for eons, the sun will warm the earth for billions more years. There is time, vast stretches of it, for life to evolve, for civilizations to rise, for discoveries to be made. The ultimate fate of the universe is not a reason for despair, but a reminder of impermanence, a call to appreciate the present. To ponder the void is also to reflect on limits. There are horizons beyond which we cannot see, mysteries we may never solve. The void is shaped by dark matter and dark energy, substances we do not fully understand. It exists in a universe whose fundamental laws we are still uncovering. The void reminds us that knowledge is finite, that there are questions without answers, at least for now. And perhaps that is part of the meaning, that there will always be more to discover, always deeper layers to uncover. The void also suggests a meaning about diversity. The universe is not uniform, but structured, with filaments, walls and voids, creating a rich tapestry. This diversity extends to galaxies, to stars, to planets, and perhaps to life. The void, as an extreme environment, produces galaxies that evolve differently, that retain gas longer, that form stars at their own pace. The meaning is that variety is part of the cosmic design, that different conditions produce different outcomes, and that the universe is more interesting because of this complexity. There is a meaning, too, in the human capacity to understand. The Boötes Void is so large, so far away, so unlike anything in our everyday experience, that it should be incomprehensible. Yet, we have mapped it, measured it, and explained it. We have connected it to quantum fluctuations, to dark matter, to the fate of the cosmos. The meaning is that consciousness, the ability to wonder and to understand, is a remarkable phenomenon. We are part of the universe, and we can make sense of it. To ponder the void is also to consider beauty. There is an aesthetic dimension to the cosmic web, to the way filaments and voids interweave, to the symmetry of structures that span hundreds of millions of light years. The Boötes Void, with its near-spherical shape, its clear boundaries, and its profound emptiness, has a kind of elegance. The meaning is that the universe, for all its indifference, is beautiful. And that beauty is something we can appreciate, even if we did not create it. The void invites existential reflection. It forces us to ask where we fit in a cosmos so vast and so old. It challenges us to find meaning without cosmic assurance, to create purpose in a universe that offers none. This is not easy, but it is also liberating. It means we are free to define our own significance, to live according to our own values, to make our own meaning. The void does not give us answers, but it gives us space to ask questions. As you rest with these thoughts, imagine the Boötes Void not just as a structure in space, but as a mirror for reflection. It shows us our smallness, but also our capacity. It reveals our ignorance, but also our progress. It presents a universe without inherent purpose, but also one filled with possibility. The meaning of the void is not fixed. It is something we each determine for ourselves, shaped by our own perspectives, our own values, our own lives. Every story has an ending, but some endings are also beginnings. The story of the Boötes Void, of its discovery and study, does not truly end. It continues, carried forward by each generation of astronomers, each new survey, each observer who looks up at the sky and wonders. The legacy of the void is not just in what we have learned, but in how it shapes what comes next. The legacy lives in the observatories scattered across the Earth, perched on mountaintops, nestled in deserts, orbiting in space. Each one is a testament to human curiosity, a monument to the desire to understand. The Boötes Void was discovered with instruments that now seem primitive, but each new generation of telescopes adds detail, depth, and precision. The legacy is continuity, the passing of knowledge from one era to the next. The Void's legacy also lives in education, in classrooms where students learn about large-scale structure, about redshift surveys, about the cosmic web. These students will go on to conduct their own research, some discovering new voids, others developing new theories, others building new instruments. The knowledge spreads, the understanding deepens, and the void remains a touchstone, an example that connects past discoveries to future ones. The legacy lives in the questions that remain unanswered. What is dark energy? What is dark matter? Are there voids even larger than Boötes, waiting to be discovered? These mysteries are the inheritance of future scientists, the challenges they will tackle with new tools and new ideas. The legacy is not closure, but openness, the recognition that there is always more to learn. The story also loops back to where it began, to the quiet wonder of looking up at the stars. Every discovery, every equation, every measurement starts with that simple act. Someone looks upward, sees something they do not understand, and asks a question. That is how the Boötes Void was found, not through grand theory alone, but through patient observation, through mapping galaxies one by one. The legacy is the continuity of wonder, the thread that connects ancient stargazers to modern cosmologists. To look at the night sky now, knowing what we know, is to see it differently. The stars are not fixed points, but participants in a vast structure. The galaxies are not isolated islands, but nodes in a cosmic web. The Boötes Void is invisible to our eyes, but it is there, shaping the distribution of light, defining the architecture of the universe. The legacy is this transformed vision, this ability to see time, motion, and structure written in the heavens. The legacy also lives in the way we think about endings. The universe will not last forever in its current form. The void is expanding, galaxies are receding, and in the distant future, emptiness will dominate. But that distant fate does not diminish the present. It enriches it, adds urgency and beauty to the time we have. The legacy is the recognition that impermanence is not a flaw, but a feature, that the fleeting nature of things makes them precious. There is also a legacy of humility. The Boötes Void has shown us that we are not the centre, not the purpose, not the point. We are one species, on one planet, in one galaxy, among hundreds of billions, living in an era when voids and filaments define the cosmic landscape. This could be diminishing, but it is also freeing. It means we do not carry the weight of cosmic significance. We are free to make our own meaning, to find our own purpose, to live our lives without needing the universe's approval. The story loops back, too, to the people who made it possible. The dreamers, the observers, the theorists, the technicians, their names are remembered in papers, in observatories, in the histories we tell. But their true legacy is not in monuments. It is in the knowledge they created, the doors they opened, the questions they inspired. Every time someone studies the void, measures a redshift, or contemplates the cosmic web, they walk in the footsteps of those who came before. As the universe continues to expand, as galaxies recede, as voids grow larger, the story of the Boötes Void continues to unfold. New observers will arise, new instruments will be built, new discoveries will be made. The void will remain a benchmark, a reference point, a structure that tests our understanding and challenges our models. The legacy is alive, evolving, just as the cosmos itself evolves. The return is to the beginning, to the simple act of wonder. After all the science, all the mathematics, all the philosophy, there remains the night sky. It is still there, still vast, still beautiful. The Boötes Void is still there, still nearly empty, still one of the most extreme features of the cosmos. The stars still shine, though we now know they are temporary. The galaxies still glow, though we know they are receding. The universe still invites us to look, to ask, to wonder. This is where the story rests, not in a final answer, but in a return to curiosity. The Boötes Void is not a puzzle to be solved, once and forgotten. It is an ongoing conversation, a relationship between humanity and the cosmos. The legacy is that conversation, carried forward by every person who pauses to look upward and asks, "What is out there?" As you let your eyes close, as sleep approaches, picture the Boötes Void one last time, a vast bubble of near emptiness, 330 million light-years across, carved by gravity, stretched by dark energy, populated by a few isolated galaxies. It is there, in the constellation Boötes, invisible but real, mapped and measured, understood yet still mysterious. The void is a reminder that the universe is larger than comprehension, that absence is as structured as presence, that emptiness can reveal truth. It connects quantum fluctuations to cosmic architecture, the earliest moments to the distant future, the visible to the invisible. It is both a scientific fact and an invitation to wonder. The legacy of the Boötes Void is yours now. The knowledge, the questions, the sense of scale and connection. As the universe expands, as the void grows, the story continues. And you, resting here, are part of that story. A brief moment of consciousness in a cosmos that stretches beyond measure. The journey through the Boötes Void has brought us full circle, from discovery to understanding to reflection. And now, as the night deepens, the story becomes a lullaby. The void drifts silently through space. The galaxies recede, and the universe unfolds according to laws we are still learning. You, resting here, are connected to it all. The legacy is wonder, the return is peace, and the void, vast and nearly empty, shines on.